All right, it's time for us to go ahead and get started. So I'm trying to unload graded homework. So after class today, if you think we have 1 through 14 for you, please pick it up. You'll get an extra credit point on the exams. Okay, so some things I wanted to talk about, and I also wanted to warn you. So I'm recording this lecture because I screwed up this morning. I would be saying the right thing, but I would write the wrong thing. And then whenever I wrote the wrong thing, I said the right thing. So it just got confusing. So if that happens this afternoon, point it out and tell me to take a deep breath or take a shot. Yeah, that sounds good. That sounds good. My brain's thinking about things it shouldn't be thinking about. All right, so I'm out of the office on Monday, so I can't hold office hours. Picking up graded homework, you'll get an extra credit point added to the ACS and the final exam next week. End of semester evaluations, those are due on Sunday. You get extra credit point as long as you complete them before the deadline and do all 3 of them. And then tomorrow or Friday, there'll be an in-class quiz that we've talked about previously. All right, there'll be a review session right after this class on Friday and then Sunday afternoon. We're going to try to get those recorded and posted as we've done on the previous ones. Final exams, we know when they are, next week, Tuesday and Wednesday. All right, so let me talk a little bit about the standardized exam. Please bring a non-programmable calculator. All right, this is an ACS rule, it's not my rule, and I have to follow them. Bring a number 2 pencil. All right, you can't use your cheat sheet. There's going to be 50 questions. The exam's designed to take about 100 minutes. I've been told that I can be flexible with the timing, so if you want to take more, that's fine. But we're going to call it at 9 o'clock. All right, that's as late as we can stay. All right, and I'm guessing that by that time, most of you will be just sick of looking at the exam. All right, you'll be given all the needed constants and the van der Waal equation. There are not other equations that are given to you. The exam overall is not calculation heavy. It's concept heavy. How many people have looked at the study guide? And you probably got the impression from that. A few calculations are pretty straightforward, but most of it's interpreting some things. And there are some equations that you do need to know. And I can't tell you what they are, but the big ones, you should know, what the first law of thermo is, right? That kind of stuff, right? And unfortunately, in the course of the exam, because it's testing, I can't clarify a question, right? So you can't really ask questions about the exam. So we're just going to be there to make sure that you're not cheating and that you don't steal the exam, all right? Any questions about that stuff? All right, I also wanted to mention something. This is not in your textbook, but I did want to define some terms. So how many people have heard of exergonic or endogonic before? Does anybody know what they mean? It's related to heat, but it's more general than that. All right, so exothermic and endothermic is about heat transfer. All right. Exergonic means that energy can be released by the process under the conditions that you're operating. So for our purposes, that means delta G is less than 0. All right. And if I'm talking about endogonic, whatever it is, delta G is greater than 0. And this is especially important in biochemical processes because in general, you don't want to transfer all of your energy just into heat. You want to be able to put it into other uses. So this just says you have a process that produces energy versus one that requires energy in order to occur. Does that make sense? Okay. All right. And then the last time we met, we talked about delta G of mixing for a non-ideal solution. We basically saw that it's equal to delta G of mixing for an ideal solution, and then we have a deviation from ideality, which we call the excess Gibbs energy of mixing. And that's determined by the activity coefficient. So we've pointed out that when the activity coefficient of our solution is less than 1, or the components of our solution is less than 1, we see a reduced vapor pressure, all right? And that we can say is due to stronger interactions between the two substances that are mixing, all right? And that leads to a negative natural log of the activity coefficient, which ultimately leads to a negative excess Gibbs energy of mixing. So if I take two liquids that interact strongly, we not only have the driving force just due to mixing of an ideal solution, but we have the enhanced driving force due to the excess Gibbs energy of mixing. If I have disruptive interactions, weaker interactions between the solvent and the solute, then we see an enhanced vapor pressure. The activity coefficient is greater than 1. The natural log, therefore, is going to be greater than 0. And our excess Gibbs energy of mixing is positive. I still will form a solution as long as the magnitude of this is less than the magnitude of the ideal mixing Gibbs energy, right? Because I still have a negative delta G overall. But as soon as this becomes larger in magnitude, then I don't get mixing anymore, and then I have immiscibility between the two. So we've said that this really explains whether things dissolve or not, right? We also talked about the equilibrium constant, and one of the things that we recognize is through our derivations is that the delta G of the reaction is the minimization of the Gibbs energy of the reactants and the products, right? So it's the minimization dG d extent of reaction d psi, right? We're also going to utilize this relationship. So when delta G is equal to 0, delta G naught, that's going to be the Gibbs energy for all the reactants and products being present at 1 bar plus RT-ln-K. This basically says if I know this number, I can calculate the equilibrium constant, right? And that probably showed up in Chem 178 or Gen Chem 2, all right? So delta G naught, as we will see today, we can determine that using Gibbs energy changes of formation, because we know that the delta G of formation will be delta H of formation minus delta S for the formation reaction, or times T, right? So we can, in principle, calculate that. And of course, we'll see that we can get the equilibrium constant then, right? We also talked about extent of the reaction and that relationship with regards to the equilibrium constant K. Homework 15 has a question that relates to this as well. And we use that to show Le Chatelier's principle, right? And then where we ended last time was we had introduced our equilibrium constant in terms of pressure, and then we showed that we could also do it in terms of molar concentration with that as our conversion factor between the two, right? All right, so some of what we're going to cover today is review from 178. This first part, there's a relationship between KQ and delta G, all right? And we'll see that that allows us to determine what the spontaneous reaction direction is. We're also going to talk about temperature dependence of the equilibrium constant. We'll go from there to discussion of non-ideal behavior and equilibrium constants. And we're going to do the same sort of thing that we've done before. We take an equation that we've derived for an ideal situation, and we're going to replace one of the components with non-ideal. So we're going to put activity in there, all right? The other thing is, and I'm certain that this is going to really perk everybody up. So back in Gen Chem 2, when you talked about equilibrium constants and you did calculations of equilibrium, you put in concentrations, you put in pressures, but if you had a pure solid or a pure liquid, what did you put in? You put 1 in there, right? So we're going to see why you use 1 today, okay? And I'm sure that everybody's been, insomniacs, wondering what that's been like, why that is, since you took 178. All right, and then the other thing that we're going to do is we're going to end by going into chapter 12, talking about non-volatile solutes being dissolved in liquids. All right, so just a little preface there. If I have a non-volatile solute, what does that mean in terms of vapor pressure? It's going to have no vapor pressure, all right? Non-volatile means it doesn't want to evaporate, okay? All right, so some things that we're going to use. We've previously derived the Gibbs-Helmholtz equation, so we're going to use this. Just a little foreshadowing here. Delta G of the reaction over T, the change of that with respect to T, is given by this. we are going to say, we know that delta G naught is equal to minus RT ln K. So we're going to replace that, and that will get us our dependence of the equilibrium constant on temperature. We're also going to look at the pressure dependence of the chemical potential. So the chemical potential of a component is given by chemical potential whenever it's present at 1 bar plus RT, natural log of the activity. This is a little bit new for us. So in this expression, we're going to say the activity for a liquid is simply the activity coefficient times the mole fraction. That we've covered before. But deviation from my ideality for gases, we're going to replace the activity now with a fugacity reference to 1 bar. Okay? And then the only other thing is that the change in the chemical potential with respect to pressure is the molar volume. We're going to use that in a derivation. And this can be rearranged to say D, the change in the chemical potential is given by the molar volume times the change in the pressure. Okay? All right, so section 12.3, basically in this section we're going to say delta G naught of formation. So the Gibbs energy change for a formation reaction can be used to determine delta G of a reaction. All right? This should be, quite familiar to you at this point, right? That's going to be using Hess's law. And then from there, we're going to show that we can get the equilibrium constant Kp. Okay? All right. So we know that we can go into tables that have enthalpies of formation of reactants and products. We can find standard molar entropies, and that means I can take that information and calculate delta G naught. Because that's easily calculable, that also shows up in tables of thermodynamic data. So when you go into appendices or online, you have substances, you've got delta G of formation, delta H of formation, standard molar entropy. So this column should be in there. I've left one out, so let's talk about that real quickly. What's delta G of formation for O2? It's going to be 0 because, again, this is referencing formation reactions. So this says 1 mole of O2 to 1 mole of O2. There's no change associated with it. Okay? All right. And for the same reasoning that we could calculate delta H of a reaction, we can calculate delta G of the reaction by looking at the Gibbs energy change for the formation reactants of the products times the coefficient from the balanced reaction equation minus those of the reactants times the coefficient of the balanced reaction equation. So that also should be quite familiar to you, right? Because this example is one that you did back in Gen Chem 2, we'll go through it pretty quickly. So I want to know delta G naught for this reaction. So 1 mole of methane with 2 moles of oxygen combusting to form carbon dioxide and water, right? So I go to my table of data and I find the Gibbs energy change for water whenever it's in the gas phase, minus 229 kilojoules per mole. And then I need to multiply that by 2 moles, right? Because that's what I've got in the balanced reaction equation. Similarly for CO2, and these represent the products, and then I subtract the Gibbs energy changes for the reactants, right? And calculating that all out gets me minus 801 kilojoules per mole, all right? So I did want to just take a moment to point out something. This tells us spontaneity only whenever all of our reactants are present at 1 bar and the products. So I have a mix of 1 bar methane, 1 bar oxygen, 1 bar H2O, 1 bar CO2. Under those conditions, we can say that it's going to be a spontaneous reaction, all right? So it's not general. Okay, but what we can do from there is say, well, we know that because delta G is equal to 0 for our reaction, at equilibrium, that delta G naught is equal to minus RT ln K. All right? And that basically says if I calculate this delta G, I can determine the equilibrium constant. All right? So I can rearrange this equation and say the natural log of the equilibrium constant is given by negative the Gibbs energy change for the reaction over RT. And to isolate the equilibrium constant, I take the exponential of both sides. So it's e to the minus delta G of the reaction over RT. Okay? And that gets us equilibrium constants. All right, any questions about anything we've covered before? And that all looks familiar, I assume. Yep. All right. So sections 5 and 6 I'm covering together. Section 6 is about, what is that about? Probably doesn't matter. I know what they are covering, but I don't know the order that they're covering them. All right. So sign delta G of reaction determines spontaneous direction. All right, and the other thing that determines the spontaneous direction is the ratio of Q over K. Okay? All right. And let me just mention something qualitatively before we talk about this in greater detail. So Q and K, same functional forms. They're going to be the concentration or the pressure of the products over the concentration or pressure of the reactants, right? So if Q is larger than the equilibrium value, that says that we have too much product, right? And that tells us that we're going to be going in what direction? Backwards, okay? All right. So we'll see that more explicitly in a moment, but I wanted to make sure that it made sense at a gut level. All right. So what we know is that delta G of our reactions given by delta G naught plus RT ln Q. We know at equilibrium that we have this equality that relates the Gibbs energy for everybody present at 1 bar and the equilibrium constant. So I basically can substitute this in for delta G naught. All right. So rewriting the equation, I can say that delta G of our reaction is RT ln Q, right? So that first term is this one. And then I need to include delta G naught, and that's minus RT ln K. All right? And then we look at this and we say, well, we've got the natural log of two different functions, both multiplied by RT, so I can combine those into one ratio. So this becomes RT ln Q over K. Okay? All right, so the easy one to see is if Q and K are equal to each other, this ratio goes to 1, and the natural log of 1 is, and that tells me I'm where with respect to equilibrium. I'm at equilibrium. Right? So delta G equals 0, and the reaction is at equilibrium. Right? And then we look at the case where Q is greater than K, then the natural log of Q over K is a positive number, right? And therefore delta G is greater than 0. And as we've said at the outset, this means the reaction is going to be spontaneous in what direction? Reverse, right? All right, and then if I have the situation where Q over K is less than 1, or Q is less than K, then delta G will be less than 0, and the reaction is spontaneous in the forward direction. All make sense? Okay? All right. We're going to be talking about the same thing, but now looking at it more graphically. So we're going to look at the Gibbs energy versus the extent of the reaction. Okay? All right. And specifically, we're going to look at two reactions. We'll go through one a little bit more carefully. So this is N2O4 going to NO2. All right? And what we've got plotted is the Gibbs energy as a function of the extent of the reaction. All right? And so basically, let's do a little reminder. If I'm at 0 for extent of reaction, what do I have present only? I only have the reactants, right? So this will be only N2O4 along this axis. And if I'm talking about this axis, I'm going to have only NO2, the product, right? And consistent with what we've said since we've introduced Gibbs energies, systems move in a direction to minimize the Gibbs energy, which means that no matter where I start, I'm going to end up at this minimum. Right? So minimum G, function of extent of reaction, is going to be equilibrium. Right? And that means that Q is equal to K, and delta G of the reaction is equal to 0. Okay? Right. And then in terms of what we've discussed about Q versus K, if I'm sitting in this region to the right, if I'm sitting further than the extent of the reaction at equilibrium, we've got too much product. So Q over K is going to be greater than 1. All right? And that tells me that delta G of the reaction in this region is going to be positive. And that also tells me that the direction of the reaction will be to approach equilibrium. So I'm going to go back down this way. Okay? Right. And then if I start on the other side of the extent of the reaction at equilibrium, then I have a situation where Q is less than K. Delta G of the reaction is less than 0, and my spontaneous direction is towards equilibrium. Does that make sense? Okay? All right. This down below, I just wanted to show another example. It's the same thing. I actually pulled this out of the 178 textbook from not last year, but 2 years ago. So this is looking at nitrogen and hydrogen reacting to form ammonia. So at this end, I've got only nitrogen and hydrogens. At this end, I've got the ammonia, a 100% product. And if no matter where I mix, I expect that I'm going to move to this direction to minimize the Gibbs energy. Over here, it's going to be the reverse reaction. Over here, it's going to be the forward reaction. Yeah?
Is it right to say that the delta G of the reaction is actually proportional to the slope of that graph above?
Yeah, I would say that that's the case because dG is equal to 0 at equilibrium, right? Does that make sense? Yeah. Yeah. Yeah, it is. Well, no, because no, I think it is, right? Because if I was looking at 2 points on there, the difference between the 2 points will get me delta G, all right? And so if you limit it to the slope, then you're just looking at dG at 1 point. Yeah. Okay. Okay. All right. So next up, we're going to look at temperature dependence of the equilibrium constant. Okay? All right. And our starting point is we have this relationship between delta G naught and the equilibrium constant. And we've previously shown that the Gibbs energy dependence on temperature is given by this Gibbs-Helmholtz equation. The derivative with respect to T of delta G over T gives us delta H over T squared. Okay? So all we're going to do is we're going to substitute this in for delta G naught. Okay? So left side, this is going to be the derivative with respect to T of minus RT ln k function of T divided by T, right? Because that's delta G over T, right? The T's are going to cancel. And I've got a negative R. I can pull those out front, right? Negative of negative becomes a positive. And I'm left with this relationship. The derivative of the natural log of the equilibrium constant with respect to T is delta H over RT squared, right? And then this integration we've done previously, right? So I can take this and rearrange it so that I've got the change in the equilibrium constant and the change in the temperature on the other side. Right? The first thing we'll do is an indefinite integration. So integrate. Right? So pretty straightforward. Left side's going to become natural log of k plus a constant. Right? And then the right side, well, if we assume delta H is not a strong function of temperature, delta H and R can be pulled out front, and I've got the integral of 1 over t squared. That's going to be minus 1 over t, and that's what we've got, plus a constant. And I lump both constants together on the right side. Right? And then if we take a look at this, we realize, calling this y, calling this x, I expect linear behavior. And what's my slope? Let's do it this way. I've got 1 over t down below. I've got the natural log of k. So this is y. This is x. What's delta A? What's the slope? Right. Slope equals minus delta h over r. Okay? Does that make sense? All right. Well, let's talk a little bit about this a little further. So the first question that I have for you is this slope, is it positive or negative? It's negative, right? That tells me that delta H has to be positive, all right? So for this, delta H is greater than 0. And is that an endo or exothermic reaction? Endothermic. Which means that we need to put energy into the system in order, heat energy, to get it to go. Okay? All right. Next up, for this endothermic reaction, we can ask what impact does changing the temperature have on the equilibrium constant? All right? So that means we need to know which side, left side or right side, is the higher temperatures. Help me out. Which side's the higher temperature? So this is reciprocal of temperature, so as temperature goes up, that gets small. So this is going to be high temperature. This is going to be low temperature. Okay? And so what that says is that as I increase the temperature, the equilibrium constant goes up. Okay? All right, and that's what's said down below here. In this example, as T increases, Kp goes down, the reaction is endothermic. All right? So if I have an exothermic reaction, we would expect a positive slope. All right? So let me go ahead and write that down too. We'll put this up in the corner up here. Running out of space. So I've got 1 over t, natural log of k. Now I'm going to put a positive slope in there. Again, the slope is equal to minus delta h over r. The fact that this is a positive slope tells me delta h has to be less than 0. And this is not endothermic, but exothermic. Okay? And what we can conclude from this is that as I increase the temperature for an exothermic reaction, that leads to a decrease in the equilibrium constant. Right, and that's summarized down below. If the reaction is exothermic, Kp decreases as the temperature increases. And if it's endothermic, then we see an increase in the equilibrium constant. Okay? Yeah? Oh, yeah. Remember how I said before that I would say one thing and write another, or I would write one thing and say another? That's a case of it. So you guys forget that I did it, I'm going to pass sugar around. At least I only did it once in here today. Okay? This morning it was filled with it. And then it became filled with expletives. All right. So I did want to talk about this in terms of the Chatelier's principle. And I wanted to just review something that you may have talked about when you took general chemistry. So I'm going to have an equilibrium reaction, reactants to products. If it's an endothermic process, endothermic reaction, which side do I need to add heat to? It needs to be a reactant, right? Plus Q, right? So this is endothermic. So for an endothermic process, we can reason this by saying, if I increase the temperature, I'm adding heat to the system, right? And the system's going to respond by trying to offset that change, which means it's going to try to remove the heat. And that means it goes towards the reactant side, right? We aren't governed by a constant, an equilibrium constant. This time, the equilibrium constant goes up, right? And if I do an exothermic process, it'll be R in equilibrium with the product plus Q, exothermic. And in this case, we see equilibrium shifting towards the reactants because the equilibrium constant decreases due to Le Chatelier's principle. That make sense? Okay? All right, the other thing I'm going to just talk through quickly, because we've done this sort of integral before. I did an indefinite integral, but now what I'm going to do is a definite integral. So we'll go from Kp, or ln Kp, at T1 to ln Kp at T2, which means we're going to integrate from T1 to T2, right? And once we put the limits on it, then we end up with the natural log of Kp for T2 over Kp for T1, integrating from T1 to T2, delta H over T squared, and appropriately performing that integral gets us this relationship, which again, we've seen this previously, okay? All right, but that tells us that we can calculate equilibrium constants as long as we have delta H of the reaction. All right, so in section 11, we're going to talk a little bit about non-ideal behavior. First part of it's pretty straightforward. We're going to use activities for the non-ideal behavior, okay? All right, so that means that when we go back to our delta G for our reaction, we need to define the equilibrium constant in terms of the activities. So previously we've put pressure in there, or we've talked about it in terms of molar concentration. Now what we're doing is we're replacing pressure and molar concentration with activity, all right? And the activity turns out to be the activity coefficient times the mole fraction if I'm talking about a liquid or solid phase, all right? If I'm talking about the gas phase, then I use the fugacity. So that'll be the fugacity of component I, reference to our standard state 1 bar, okay? All right, so that should be pretty straightforward, right? The other thing that we want to do is to extend this a little bit and ask the question, why is activity taken to be 1 when we have a pure solid or liquid, or so a pure condensed phase, okay? So this is going to be a quick, easy derivation. We're going to start with the chemical potential, right? So we have our chemical potential at any temperature and pressure. That's going to be the chemical potential at that temperature at 1 bar plus RT, now the natural log of the activity. If I differentiate that, that's going to get me the differential of the chemical potential, which is now a function of pressure for component J, right? So the reason that I left out temperature in this is that I'm saying I'm holding the temperature constant. So it's not changing. So I only am thinking about the chemical potential as a function of pressure, right? And that in turn will be the differential of the right side of this. This is a constant at a given temperature. So the differential of a constant is 0. And R and T are both constants, so those come out separately. And we might expect that our activity now is what's going to change. Right? So I have the differential of the natural log of the activity. Okay? All right. And I can rearrange this and say that the derivative or the differential of the natural log of the activity will be given by the differential of the chemical potential over RT. Okay? Right? So I've just rearranged this equation. Right? Okay, so the other thing we can do is we can say, well, we know that the change in the chemical potential due to a change in pressure is the same as the molar volume. So I've got this relationship, and then I can rearrange that and say that the differential of the chemical potential is the molar volume of the component times dP. Okay? All right. And now this is the same as this. So I can do a substitution. Okay? So d ln A is going to be the same as V bar J dP over RT. Okay? All right. And in order for me to get the relationships, I'm going to need to integrate. Right? Because I'm specifically talking about condensed phases, we look at the integral and say, well, what can we pull out? Right? Well, if it's a solid, and if we're not changing, or a liquid, we don't expect the molar volume to change due to pressure. Right? They're pretty incompressible, so I can pull that out front. So that's going to get me V bar J over RT, and then the integral of dP. Okay? Now we need to know what limits to integrate over. Right? So what we're going to do is we're going to say, if I have a pure liquid and a pure solid, I'm going to say that the activity's reference is 1 whenever I'm at 1 bar. Okay? All right, so that says that I'm going to integrate from AJ equals 1 up to A. All right? And then my integral over here is going to be pressure 1 bar up to some other pressure. Okay? All right, so let's look at the first side of this. The integral of d ln A is going to be ln A. And the limits are AJ and 1. And what's the natural log of 1? 0. All right, so that means the left side of this integral is simply the natural log of the activity. Okay? And then I go to the right side of this, right? And we see that that's just going to be the integral of dP, which is delta P, right? So that's going to be V bar J over RT times P minus 1. Okay? All right. So you may not have thought much about this whenever you were doing the calculations in Gen Chem 2, but what sort of pressures were you normally operating at? 1 atmosphere, 1 bar, right? And when I'm at 1 atmosphere, 1 minus 1 gives me 0. Natural log of AJ is equal to 0, which means AJ is equal to 1, right? So this is all about the reference point for 1 bar, okay? All right, so let me write that. So at P external equal 1 bar, ln AJ equals 0, and therefore the activity is equal to 1. Okay? All right, so what we're going to do next, I'm going to have a blank page. We're going to come back to that in a moment. In chapter 11, we're going to be talking about dissolving non-volatile solutes into liquids. Okay? All right. And non-volatile solutes are or I would say solids are characteristic. So we're talking about liquid solid solutions, okay? All right, and then I just wanted to make sure that we point out explicitly that non-volatile means P vapor, the vapor pressure for the solute, will be equal to 0, okay? That'll make sense? Okay, so let's go back and see what impact this has. All right, so for our solid liquid solution, I'm going to start by looking at a graph of pressure as a function of the mole fraction of the solvent. And that'll go from 0 to 1, okay? All right, so if I have no solvent present, there's going to be no pressure due to that solvent, right? And when it's 100% solvent, then I'm going to have the vapor pressure of the pure solvent, which is P star. If we assume ideal behavior, what do I add to this graph? Straight line that connects the two dots, right? That's Raoult's law. We agree? Okay? All right, so one of the things that we see is that in my solution, the vapor pressure is going down due to the fact that I've added a solid. What's the vapor pressure of the solid? It's 0, all right? And so that means that not only is this pressure that I've shown the pressure of the solvent, but it's the total pressure of the mixture. Okay? And if I choose to look at a particular mole fraction of the solvent, this shows that my vapor pressure has gone down, right? And so what we can conclude is that for a solid liquid solution, I see a reduced vapor pressure due to the dissolution, okay? So P vapor has gone down due to solid dissolving. And we know that there's a relationship between the vapor pressure and the boiling point. What happens to the boiling point of the solution due to adding the solid? It goes up. So the boiling point or the vaporization temperature go up. Okay? All right. And one thing to point out is it's going to go down proportional to how much I dissolve in it. Right? Okay? All right. So the other thing that this has an impact on is the overall phase diagram. So I'm going to put pressure as a function of temperature. I'm going to draw in my standard phase diagram. This in blue is going to be the phase diagram of the solvent. Okay? I've got the solid phase, the liquid phase, and the vapor phase. All right? So I'm going to take my solvent, I add some solid into it. Which curve definitely moves? Right? I'm going to say this is A, B, and C. Which curve moves? We know the vapor pressure is going down, right? So that means this slides down. Okay? So I'm going to draw in a curve, connect to the solid line, right? This is the solution. Okay? Clearly what we see is there's the vapor pressure decrease. Right? The boiling point increase will be looking at this point to that point, right? Because the boiling point would be at the same pressure. So this is delta T boiling point. And I just want to point out that T boiling point of the solution goes up. Okay? The other thing that we notice is that we have a new critical point. And if I have a new critical point, that means my other coexistence curve also shifts, right? So I have a new liquid-solid coexistence curve, right? So what's happened here? You have a reduction in the melting point, right? Delta T of fusion, or T melting, or T fusion, both decrease. Okay? All right. And this, you've probably heard this before, but this is why you put salt on, the sidewalks in the winter. It reduces the melting point. Okay? All right. So these properties that we've introduced are called colligative properties. All right? So examples of colligative properties now are vapor pressure reduction, boiling point, TBP, elevation, and melting point, reduction. Okay? All right, and there's another colligative property that I'm not sure that we're going to have time to talk about, but it's osmotic pressure. Okay? All right, so the one thing I haven't done yet is I haven't talked about what we mean by a colligative property. Okay? All right, so if I come back to this vapor pressure diagram, right? This small fraction here is due to whatever my dissolved solute is. And we don't care what its identity is. So we don't care if it's sugar. We don't care if it's salt. We only care about its amount of dissolved substance, right? That's what a colligative property is. It depends only on the amount of the dissolved substance and doesn't care about identity. But we do need to be a little bit careful when we're talking about this. So I wanted to take a moment to just look at some solutions that would behave the same. All right. So we're going to be talking about aqueous solutions. And what do ionic substances that dissolve in aqueous solutions do? They dissociate. All right. So if I have a 0.1 molar NaCl solution, when that dissolves, or that forms 0.1 molar Na plus and 0.1 molar Cl minus. So this is 0.2 molar dissolved species. And that would be equivalent to 0.2 molar glucose. Because glucose does not dissociate when it dissolves, right? And if I was dissolving FeCl3, then I would get 4 times 0.1 or 0.4 molar, all right? But this emphasizes the idea that it depends upon the number of dissolved particles and not their identities, all right? Does that make sense? All right. We're going to pick up there on Friday. We have a little bit of new material. We'll have a quiz on Friday, and then we'll celebrate by letting you go home. All right. Well, you'll see, hopefully, most of you tomorrow night. Yeah. Have a good evening. Again, I have graded homeworks. If you would like to pick them up, please do so.